Alright, so this is our AP Chemistry Chapter 8 lesson video part 3, and we are going to finish up with section 8.6 through 8.8. Alright, so we ended with Lewis dot structure on our last video, so now we're going to focus on, and we did formal charges, so now we're going to focus on resonance structures a little more. So you already saw some resonance structures when we did formal charges, and so resonance structures are just when more than one possible Lewis dot structure can exist for a substance. So resonance structures in which the position of the atoms are the same, but the placement of the electrons is different. Okay, so you can't move any of the atoms, you can only move the bonding and the lone pairs and things like that. Neither structure is correct on its own, and the structure does not oscillate between the two. So resonance is a little bit tricky to understand. A true structure is a hybrid of the two structures, or it could be more than two, it could be three, because experimental evidences show that the OO bonds and O3 are of equal length. Okay, so when you try to draw O3, which is just ozone, you could have a double bond on one side, or you could have a double bond on the other side. So that would give this a bond order of 2, and this a bond order of 1. And then sometimes this would be a bond order of 1, and this would be a bond order of 2. Well, it's really a hybrid of the two. So what we say is they each have a bond order of 1.5. And like I said, it doesn't oscillate between the two, it's a hybrid of the two. So it's kind of like when you have yellow and blue and you mix them together and make green. It doesn't just keep flashing yellow and then blue sometimes. It's just a hybrid of the two colors. So that's what happens when resonance occurs. So in writing resonance structures, the same atoms are bonded to each other, so the only difference is in the arrangement of the electrons. The resonance structures are separated by a double-headed arrow. So you can see that the C, the H's, and the N's, they're all in the same position, but all that has happened is one of the bonds is here in this structure and one of the bonds is here. Now again, it's a hybrid of the two. So it's not like this is a single bond and this is a triple bond sometimes, and then sometimes they're both double bonds. What we would say is this has a bond order of 1.5 because it's 1 and 2. And this would have a bond order of 2.5 because it's between a hybrid between a 2 and a 3, like that. All right, so let's look at the first one together. So it says, which is predicted to have the shorter sulfur-oxygen bond? So remember, the way you can tell the difference in bond length is how many bonds. So the more bonds something has, the closer the atoms pull together. So we're looking at SO3 or SO3 negative 2. All right, so let's look at SO3 first. So S has 6 valence electrons, O has 6 times 3 for a total of 24 valence electrons. So when I draw it, I'm going to put S in the middle because it's the single atom. I need to give everybody an octet, so O has 2, so it needs 6 more. This O has 2, so it needs 6 more. And this O has 2, so it needs 6 more. And then sulfur has 2, 4, 6, so it needs 2 more, just like that. The problem is, when I count up, I have 26 valence electrons. So I have 2 extra electrons, so I need 1 bond. Now the problem is though, I can put the 1 bond in any of the 3 locations. So this has resonance. All right, so I'm just going to choose to put it right here. So I remove a pair from each of the atoms that I added that bond to. But the problem is, it could also look like this. Or it could also, I need to get a new marker. Sorry, I didn't need any dots on this. Look like this. And formal charges can't distinguish between these 3 because it's all the same elements. Alright, so that means it's a hybrid of the 3. So when I try to say what the bond order is for this one, it's a single, a double, and a single, hybridizing. So it's like a 1.3 bond order. So the bond order for this one is like 1.3. Okay, because when you take a single and a double, which would be a 1 bond order and a 2 bond order, you get 1.5 because it's halfway between. But if we have a single, a double, and a single, so like 2 singles and 1 double, it's 1.3 bond order. Alright, so now let's look at SO3 negative 2. So SO3 negative 2, S has 6, O has 6 times 3, but I'm going to add 2 extras because of that negative 2 charge. So I have 26 valence electrons. So I put S in the middle, bond all my O's. So this O needs 6, this O needs 6, this O needs 6. S has 2, 4, 6, so it needs 2. Now, unlike here, when I added those two, I had too many electrons. Now, I'm allowed to have 26. So this is the structure. So in other words, this is just a single bond. So the bond order for this one is just 1. So it says which is going to have the shorter. The higher the bond order, the shorter it is, because like a single bond will be longer than a double bond, longer than a triple bond. So a 1.3 bond order will be shorter than a 1 bond order. So the shorter one would be SO3, just like that. All right, so you just got to figure out what those hybrid bond orders are when you have resonance. All right, so there we go. So y'all try the next one. I'll assume you've done that, and we'll look at it together. So it says, draw the two equivalent resonance structures for the formate ion, which is HCO2 negative. All right, so H has 1, C has 4, O has 6 times 2, and negative means plus 1 more. So I have 12, 13, 14, plus 4 is 18 electrons to work with. All right, so this one, H can't be in the middle because, of course, it can't have more than one thing bond to it. So C is actually going to be in the middle, and the H and the O's are going to bond to the C. All right, so it's going to look kind of like this, like we're going to have H, O, O, like that. All right, so H doesn't need anything else because, of course, it only has a duet. All right, O has 2, so it needs 6. O has 2, so it needs 6. C has 2, 4, 6, so it needs 2 more. But the problem is, I'm only allowed to have 18. I have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So I have 2 extra electrons, so I need 1 bond. So I could put it here or here. I can't put it here because hydrogen cannot accept more than a duet. So I'll put it here, so I take away a pair of electrons from each atom that new bond touches, and then because it is a polyatomic, oh, I forgot to bracket in the one on the previous page. I just realized that SO3 negative 2. That should have had brackets and a negative 2. And so then it would also be possible to do it like, this, to put the double bond with the other oxygen. And just make sure as you move that double bond, notice how I alter the electrons. So when oxygen has a double bond, it only needs 4 dots, 2, 4, 6, 8. When it has a single bond, it needs 6 dots, 2, 4, 6, 8. So notice as I changed this to a single, I gave it 6 electrons. As I changed that to a double, I gave it 4. All right, so those would be my 2 options. Oh, and that was it. We don't have to do anything else with it. All right, so the bond order, just letting you know, because some of y'all need some practice with bond order, for the CH bond would be 1, because that doesn't change. It's just a single bond. So that bond order would be 1. But because we're splitting a single and a double bond, the bond order of the CO bonds would be 1.5. Okay, and so 1 bond order would normally be longer than a 1.5, but in this case you have other variances you would have to take into account, such as the radius of the atoms, because hydrogen and oxygen are not the same size. All right, so let's move on. So benzene is something that we like to talk a lot about because we use it a lot in organic chemistry, and so you'll just want to make sure you know how to draw it. So benzene is an aromatic ring organic molecule with the formula C6H6. The resonance of benzene is represented in many ways. Okay, so when you draw benzene, it is a hexagon of carbon atoms. They each have 1 hydrogen, and in order to make sure all the valence electrons are correct, you have alternating double and single bonds. But then, of course, you could have the double bonds in the other 3 locations. So these are the 2 resonance structures of benzene. So if they ever talk about benzene, it's just C6H6. And alternating single double. So of course, because it's alternating single double, we say all of them have a bond order of 1.5. So 8.7, exceptions to the octet rule. So we've already talked about how hydrogen and helium only do a duet, but there's other exceptions to the octet rule. So the 3 main categories are odd number of electrons, less than an octet, and more than an octet. So when an odd number of electrons occurs, the central atom usually gets the unpaired electron. Okay, so like here, as terrible as that looks, I know if you are like me, I hate the odd number ones. As terrible as that looks, Nitrogen's in the center, so it's the one that has to have the odd number. If there is no central atom, the formal charges can be used to pick the correct structure. Okay, so like if we had this right here and there was no central atom, you would just do your formal charges to decide who was preferred. So we can look at formal charges right now. So N has 5, and then we gave it 1, 2, 3, 4, 5. So 5 minus 5 is 0. O starts with 6. 1, 2, 3, 4, 5, 6. So 6 minus 6 is 0. Or we can have 5 for N, but we gave it 1, 2, 3, 4, 5, 6. So it's -1. Or O starts with 6, but we gave it 1, 2, 3, 4, 5. So it's +1. So in this case, remember, formal charges, we prefer zeros if possible. So this would be the preferred structure, and N would have the odd number. And y'all, I just go ahead and tell you, N and some of the halogens are usually the ones I've seen with odd numbers. The odd numbers are very, very uncommon and terrible because nobody likes them. All right, so what happens with less than an octet? So remember, we've learned this in honors before. Molecules with less than an octet normally occur with boron and beryllium. So beryllium, because it only has 2 valence electrons, it can usually only form 2 bonds, and so that means it can only surround itself with 4 instead of 8. And then boron only has 3 valence electrons, and so it usually forms 3 bonds, and so it will surround itself with 6 electrons instead of 8. And so you just have to kind of memorize those. Okay, so beryllium tends to have 4 electrons instead of 8. Boron tends to have 6 electrons instead of 8. And so it's just based on its valence electrons. So what happens with more than an octet? So molecules with more than an octet can only occur for atoms in the 3rd period and beyond because of the d orbitals. So if there are no d sublevels, more than an octet can't happen. So in the first 2 rows on the periodic table, they don't have d orbitals yet because we don't get to d until we get to 3d. So common elements that have more than an octet are S, P, AS. Ooh, that should be a lowercase s. I hate this. I shouldn't have used this PowerPoint because the font, all the capitals, I need to lowercase that. Some of the halogens and some of the noble gases. Okay, and so you've seen these before in honors. That's how we get things like trigonal, bipyramidal, octahedral, square planar, seesaw, those type shapes. So it says draw the Lewis structure for ICl negative. All right, so let's look at this one together. So I is 7, Cl is 7 times 4, and the negative means adding 1 more. So I have 28 plus 8, which is 36. All right, so I is going to go in the middle because it's the single one. All right, so Cl needs 6 more. This Cl needs 6 more. This Cl needs 6 more. This Cl needs 6 more. I doesn't need anything. 2, 4, 6, 8. But the problem is when I count up, I only have 32. So a lot of times y'all will start trying to add multiple bonds. But remember, we add multiple bonds when we have too many. We have too few. We only have 32. We have to have 36. So when that happens, you just put your extra ones on the center atom, just like that. Okay, so iodine this time is going to have 2, 4, 6, 8, 10, 12, which is fine because it can accept more than an octet since, of course, it has those d sublevels available. All right, and then because it does have a charge, I put my brackets and my charge around it. And so, like I said, in Chapter 9, we'll start getting into the shapes of all of these things. Because remember, these are not flat, they're all 3D. All right, so y'all tried this one. I'll assume you've done that, and we'll look at it together. So it says, which of the following atoms is never found with more than an octet of valence electrons around it? S, C, P, or Br? Well, y'all remember, it can't start until the 3rd energy level. So the only one of these that's not at least in the 3rd energy level or beyond is carbon. Carbon's only in the 2nd energy level, so it will never have more than an octet. All right, then it says draw the Lewis dot structure for XeF2. So Xe has 8 valence, F has 7 times 2, so we have 14 and 8, which is 32 valence electrons. 14 and 8, yes, it's 32. All right, so Xe is going to go in the middle. So I bond my 2 F's. So F has 2, so it needs 6 more. F has 2, it's going to need 6 more. Xe has 2, 4, so it's going to need 4 more. But again, remember, we have to use, oh, sorry, this should say 22. I knew something seemed wrong with it when I first said it, and I don't know what happened. It's been a long day, y'all. A lot of lesson videos in one day. All right, so I count 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So I have to have 22, so I just put the extra 2 on that center atom. Okay, because remember, Xe can accommodate more. It's one of the noble gases. So hopefully you got that right. So in general, a Lewis dot structure where the octet rule is satisfied without using multiple bonds will be preferred. So for example, PO4 with a -3 charge. This is a whole bunch of different options of how you can do it. You could have all single bonds, you could have 2 double bonds, you could have 1 double bond, but then it has 4 different options of where it can go. So most of the time, we just prefer the one that has single bonds if possible, although that's not always what formal charges will prefer. Formal charges sometimes will prefer the one with multiple bonds. All right, so last section is strength of covalent bonds. The stability of a molecule is related to the strength of the covalent bonds it contains. So the stronger the bonds, the more stable the molecule is. The strength of the covalent bonds between 2 atoms is determined by the energy required to break that bond. The bond enthalpy is the enthalpy change, or delta H, for the breaking of a particular bond in 1 mole of a gaseous substance. Okay, so bond enthalpy is just kind of the energy needed to break a bond. So we use the designation D and then in parentheses the bond type. So what we mean is, like, I could say DCH. That would be my bond. To represent the bond enthalpies. When molecules contain multiple identical bonds, then we use the average bond enthalpy. Okay, so there's a chart in your book that has a list of the bond enthalpies. So if they were going to ask you something like I'm going to show you in a minute on the AP exam, they would clearly give you the bond enthalpies. You don't need to memorize them. I don't even have them memorized. All right. So the bond enthalpy is always a positive quantity because it always requires energy to break a bond, even if the bond is very weak. The greater the bond enthalpy, the stronger the bond. A molecule with strong chemical bonds generally has less tendency to undergo chemical change than one with weak bonds. So if you have weak bonds, when you bump into somebody else, you're more likely to react with them. If you've got nice strong bonds, you're not really interested in reacting with other things. So when you calculate the delta H of a reaction using bond enthalpies, you use the following equation. So in math, you may have seen this before. This is just summation. So it's the summation of bonds broken minus the summations of bonds formed. Okay, so a lot of times I'll just write delta H is bonds broken minus bonds formed. And that's all we're doing. Okay, bonds broken minus bonds formed. And so we're going to use the numbers, like the numbers you're going to see me write for all of these different bonds, I'm pulling from the bond enthalpy chart, okay, which, like I said, is in your book. Or you can Google one, like that works too. All right, so it says using table 8.4, so in the old book it was table 8.4, in the new book it might be something different, but it's still in there. Estimate delta H for the following reaction. All right, so let me get my paper out, because like I said, I don't have the bonds memorized, or the bond enthalpies memorized. All right, so first what I do is I go ahead and just write what bonds are actually broken and formed. Okay, so I do my delta H, and so let's see what is broken. All right, so I look over here and I see that we have some CH bonds, but we have more than one, so I have to keep that in mind. I have 1, 2, 3, 4, 5, 6 CH bonds. So I'm going to do 6 CH. Whoop. Let me do a bond in between them. All right, that's going to be broken. I have a CC bond, a single bond. So a CC single bond. All right, I have O2 bond. O2, of course, is a double bond. It's going to look like this right here. Okay, notice I haven't put any of our lone pairs. So it's going to be a double bond. But notice I have a coefficient. If you have a coefficient, you also have to multiply that by your bonds. So I'm going to have 7 halves of an O double bond O. Those are all the bonds I'm breaking. So see, I'm breaking all the CH bonds, I'm breaking a CC bond, I'm breaking an O double bond. All right, now I do minus bonds formed. So I can see over here, I'm forming a CO double bond, but I'm forming 2 of them, but I'm also going to multiply that by 2 because it has a coefficient. So I really have 4 CO double bonds. All Alright, so on this side, I'm going to do 4 CO double bonds. Alright, I'm going to form OH single bonds, but I'm going to form 2 of them. But I'm really going to form 6 of them. Okay, so you just got to make sure you're using your coefficients, the 6 OH bonds. Alright, so once I know that, then I can go look at my bond enthalpy. So those are the numbers that I'm going to plug in a little bit for you. Okay, so for the CH bond, it was 413. And so notice I multiplied it by 6. For the CC single bond, it was 348. For the O double bond, O, I'm going to keep my 7 halves. It's 495.
Good afternoon, wrestling team. Your bus is waiting for you. All those going to the wrestling match, please make your way to the bus.
All right, and so then my C double bond O was 799, but I'm going to multiply that by 4. And then my OH bond was 463, but I'm going to multiply that by 6. And so once I do all that, I end up getting negative 1,415.5, and my unit is kilojoules, because all of these numbers are in kilojoules per mole. Some of you have trouble getting all of this in the calculator correctly, so you'll notice this is like one of the only times I don't put units there for you to see. But that's what I end up getting. So just make sure you're real careful with parentheses and negatives and things like that, because you need to subtract all of this. You don't want to subtract just this part and then add that part. So make sure you're real careful with your parentheses. All right? So hopefully that wasn't too bad. The first one you ever see is kind of a little like, oh gosh, but they're not that bad. Alright, so for the second one, maybe you try this one. I'll assume you've already paused it, tried it, and we'll look at it together. Alright, so let's look at what we're breaking first. Alright, so remember, it's bonds broken. So I can see I'm breaking NH bond. But how many? 1, 2, 3, 4. So I'm going to do 4 times that. I'm also breaking an NN bond, but just one of them. All right, that's all the bonds I'm breaking. So what am I forming? I'm forming an NN triple bond, just one of them. All right, I'm also forming an HH single bond, but I have a coefficient, so I'm going to do 2 of those. All right, so then I just go to my bond enthalpy chart. So I have, oops, let me flip to the next page. So I have 4 times NH bond is 391 kilojoules per mole. And NN single bond is 163. And NN triple bond is 941. Imagine that, because that's a super strong bond, triple bond right there. And then an HH bond is 436, but I'm going to multiply it by 2. And so once I do all that, I get negative 86 kilojoules. Just like that. Okay, and you don't always get a negative number. You can get negative, you can get positive, it just depends on what's happening. Alright, so hopefully you got that one right. Alright, so bond enthalpy and bond length. As the number of bonds between carbon atoms or any type of atoms increases, the bond enthalpy also increases, so it gets harder to break, and the bond length decreases because they start getting closer together. That is, the carbon atoms are held more closely and more tightly together. Okay, so it doesn't just happen for carbon. They were just talking about carbon, and we have the carbon single, double, and triple bond right here. So as more bonds are formed, they get closer together, and it's harder to break them. In general, as the number of bonds between 2 atoms increases, the bond grows shorter and stronger, which makes sense. All right, yay, we're done with this chapter. So sample integrative exercise. So it says phosgene has the following elemental composition: 12.41% carbon, 16.17% oxygen, and 71.69% chlorine by mass. Its molar mass is 98.9 grams per mole. Determine the molecular formula. Okay, so y'all, I gotta do empirical formula first because they gave me the percentages. So remember, step 1 is change percent to grams. So I have 12.41 grams of carbon. I have 16.17 grams of oxygen, and I have 71.69 grams of chlorine. Okay, so next step is I'm going to change all of them into moles. All right, so for carbon, 12 grams is 1 mole, and that gives me 1.03 moles for carbon. For oxygen, 16 grams is 1 mole, and so that gives me 1.01 moles for oxygen. And for chlorine, 35, I did 0.5 grams is 1 mole. So I get 2.02 moles for chlorine. A lot of times in AP, I actually like to go out 2 decimal places, so that's why for chlorine I went ahead and did go out the 1 decimal place. Alright, so then next I divide by the smallest, so my smallest is 1.01. So that gives me 1 mole for carbon, 1 mole for oxygen, and 2 moles for chlorine. So that means my empirical formula is COCl2. But remember, it asked me for my molecular formula. So notice it gave me the molar mass. So remember, we just add up the molar mass for this. So when I add up this, I end up getting, oh, I didn't actually write it down. Okay, hang on, let me do it real quick. All right, so when I add up this, I'm going to get 12 plus 16 plus about 35 times 2. So that's going to give me about 98. And to see, since that's about what its molar mass is, that means I don't need to multiply it by any numbers. That just is my molecular formula also. All right, so that must be why I didn't write it down. All right, so let's go to the next part. So COCl2. So then it says, okay, so we have COCl2. So it says draw 3 Lewis structures for the molecule that satisfy the octet rule for each atom. Okay, so C has 4 valence, O has 6, Cl has 7 times 2, so 14 plus 10 is 24 valence electrons. That's what I have to work with. Okay, so here C is going to go in the center. Y'all, whenever you have C with multiple other elements, C is usually the center atom. Alright, so I'm just going to put a C, I'm going to put an O, I'm going to put Cl, just like this. Alright, so Cl has 2, so it needs 6 more. Cl has 2, it also needs 6 more. O has 2, so it needs 6 more. C has 2, 4, 6, so it needs 2 more. But the problem is I'm allowed 24, this is 26. Okay, so that means I could have a double bond here, and then take away that pair. I could have a double bond to oxygen. Or I could have a double bond to the other chlorine. Oop, I don't need 6 around that one. And so remember, make sure as you're adjusting where that double bond is, you're adjusting for the octet for each of them. Okay, I think the next one deals with these structures, so I'm not going to erase them. Right, so there's our 3 possible structures. So then it says, using formal charges, determine which Lewis structure is the most important one. Okay, so I'm going to do my formal charges. So for O, it was 6. We did 1, 2, 3, 4, 5, 6, 7. So it's -1. Cl was 7, but we did 1, 2, 3, 4, 5, 6. So it's +1. C is 4. 1, 2, 3, 4. So it's 0. Cl, is 7. And we gave it 1, 2, 3, 4, 5, 6, 7. So it is 0. All right, we come over here. O has 6. We gave it 1, 2, 3, 4, 5, 6. So it's 0. Cl is 7. We gave it 1, 2, 3, 4, 5, 6, 7. So it's 0. C is 4. We gave it 1, 2, 3, 4. So it's 0. Cl is 7. We gave it 1, 2, 3, 4, 5, 6, 7, which is 0. Oh. Saying these over and over again has to be super boring for y'all to watch. Sorry about that. I can't assume you know what I'm talking about though. Alright, so Cl is 7. We gave it 1, 2, 3, 4, 5, 6, 7. So it's 0. O is 6. We gave it 1, 2, 3, 4, 5, 6, 7. So it's -1. Cl is 7. We gave it 1, 2, 3, 4, 5, 6. So it's +1. And C is 4. And we gave it 1, 2, 3, 4. It's 0. So remember, we want one where all the formal charges are 0 if possible. And so that will be this one right here where there's the double bond to the O. Okay, because otherwise we're going to get a +1 and a -1 on those. All right, so hopefully formal charge isn't too difficult for you. It's just a little bit time consuming, and the faster you get at it, the easier it is. Okay, and see, for mine it's the first structure because that's the one with the double bond to the O. Alright, so part D. Ooh, yay, we're at the end. It says using average, ooh, I have to sneeze, so I might just excuse myself in a second. It's coming, but it won't come. Y'all know what I mean. Alright, so using average bond enthalpies, estimate the delta H for the formation of gaseous phosgene from CO gas and Cl2 gas. Alright, so y'all, we have CO gas. So CO, okay, I guess we're going to have to draw it. So C is 4, O is 6 for a total of 10 valence electrons. So I would start like this. I would make everybody stable, but I would realize, oh, I'm only allowed 10, 2, 4, 6, 8, 10, 12, 14. I have 4 extras, so I need 2 bonds. So I remove 2 pairs from each one. So there is my carbon monoxide. All right, and Cl2. So Cl is 7 times 2, which is 14. So I do Cl, Cl, I give each one 6 more, and that is 14, so that's good. And then we said we are making phosgene. So C double bond O, because remember we just decided this is the preferred structure. Alright, so we have to do bonds broken minus bonds formed. So my delta H, I'm going to break a CO triple bond. I'm going to break a Cl single bond. Minus my bonds formed. I'm going to form a CCl bond, but I'm going to form 2 of them. And I'm going to form a C double O bond, just like that. Alright, so then you just use your bond enthalpies chart. So, my C triple bond O is 1072. My CL bond, single bond, is 242. I have 2, oh hang on, let me change it to brackets. I have 2 CCl bonds, which is 328. And I have a C double bond O bond, which is 799. And so once I subtract, I get negative 141 kilojoules, just like that. Alright, so hopefully that bond enthalpy wasn't too bad. That was probably the only new thing that you didn't already learn in honors was the bond enthalpy. So remember, for bond enthalpy, just make sure if you see more than one bond, you multiply it by that amount. Or if it has a coefficient, any of those bonds, you have to multiply that by that amount. And remember, you don't have to memorize bond enthalpies. You'll either be given them, or, otherwise they can't ask you because nobody expects you to memorize them.